So I'm going to walk you through how to do the chi-square test using the table that Dr. Hall mentioned in her video. So again, here's the chi-square formula. The sum of the observed value minus the expected value squared over the expected value. So you can break this down into a table, and this is what the table looks like when you set it up. So you can record your observed for your dominant and recessive alleles. I'll show you how to calculate expecteds and drop them in here, as well as how to fill this out so you can see you can do your observed minus expected, then square it, and then do the division, and then total it all up. So this whole table has the whole equation in it, keeps it organized for you, for those of you who are like me that have a hard time making sure that everything is in a formula. So how does this work? So let's walk through a example. So here is a monohybrid cross of an ear of corn. Like Dr. Hall said, this would be normally done in the lab with ears of corn. So a monohybrid cross of two heterozygotes. So we'll talk about this in lab, in lecture. Heterozygote for different genes. So we've got two that we think are crossed with different genes. So we expect the phenotype ratio to be 3 dominant to 1 recessive. So the same ratio that Dr. Hall mentioned in her video that Mendel found. And so for this ear cross, the offspring for this cross were counted to be 2,975 individuals with the dominant phenotype, the dominant characteristic, and 1,025 with the recessive. So the first thing to do is to transfer your observed or counted individuals to the table. You'll do the same thing with this with your dragons. So when you get your totals, do the same sort of thing. So we're going to do the 2,975 for our dominant, and then the 1,025 for the observed. So now to calculate the expected values, we're going to calculate the total number of individuals observed. So in this case, it's 4,000. It comes out to a nice round number. Now to calculate this column, what we're going to do first is, so we've calculated our total number of individuals observed. We're going to add the numbers of the expected ratio to get the total number. And so I've given you examples here. So the ratio we're using here is 3 to 1. So the total number is 4. There are other ones like a dihybrid ratio for a cross like this would be 9, 3, 3, 1. So the total number would be 16. So we're going to use this one. So the total number would be 4. Now we're going to take the total number of individuals observed, so this number right here, and we're going to divide that by the number we calculated up here in step 2. So in this case, we're going to divide it by 4. So total number of individuals, 4,000, divided by 4. So that's going to be 1,000. That is the value of the 1 in the ratio for our expected column. So in this case, it's a 3 to 1 ratio. So the one that we would expect to be the 1 would be 1,000. If we were doing this 9, 3, 3, 1, this one would be the 1,000. Okay. Then using that number, so the one that we calculated for the 1, we multiply it by the matching number from the ratio for the other traits. So the matching number in the ratio for the dominant is 3. And so we're going to take 1,000 times 3, and that gives us 3,000. So that gives us our expected values. So this is what we would expect to see if the ratio is actually 3 to 1. So you can see it's close, but we still aren't sure if this is actually due to random chance or if it's actually because of the genetic makeup. So now what we're going to do is we are going to take the observed and subtract the expected. So we're going to negative 25, and then we get 25. These numbers should be pretty much the same, all right? Just one negative. Then you're going to square each of them, and it's going to be 625 for each in this case. And when you multiply two negatives, in this case, you're going to get the positive. Then you're going to take that 625. The next thing tells us to take this number and divide it by the expected. This is where you're going to get a difference. So you'll see that these columns are going to be generally the same in this case, but it's going to be a difference here because the expecteds are different. So for this one, we're going to take 625 and divide it by 3,000. And that gets us a value of 0.208. And then when we divide this one, 625 divided by 1,000 is 0.625. All right. So now we've got our observed minus expected squared divided by expecteds calculated. Now we're going to sum them. So now you just add those together. And you get 0.833. The nice thing about this table is it doesn't just keep your stuff organized, but it makes sure that you do all of the calculations. So now you've got your chi-squared. You can look up the information on the table. So we know this one is 2 minus 1 for your degrees of freedom. So it's 1 because there are only two characteristics. So you can look up, I've got the small version of the table that Dr. Hall had. So we're looking for 1 degree of freedom, 1 degree of freedom. So you're looking to see if you've got numbers greater than either of these two. Our chi-square is smaller. So since it's smaller, then we are going to have to accept or fail to reject the null hypothesis in this case. All right. So let's take a look at another example, one that doesn't have perfectly round numbers. So here, this is a test cross, and we've got smooth seeds, that's the dominant trait, and wrinkles are recessive. And we think that this was a heterozygous cross. Okay. Seeds that were collected have 22 smooth seeds, so we know that one is the dominant, and 43 wrinkled seeds. So that one we know is the recessive. Now we want to know, using chi-square, do we actually have two heterozygous plants producing these seeds? So 2 heterozygous, because we just did 2 heterozygous in the one before, we know that that ratio is 3 to 1. So that's the one that we're going to be using to figure out in this table if this is actually a cross between 2 heterozygous. So we're going to do our same steps as we did before. So 22 plus 43, we've got 65. All right, so we're going to do the same thing. We've got 4, right? Because our ratio here is still 4 if we total it up. So we're going to take 65, divide it by 4, and that means that the 1 in the 3 to 1, the recessive, we expect to be 16.25. And it is okay for the expecteds to be a decimal point, right? Because they are expecteds, so they're based on that ratio. So now we take 16.25 and multiply it by 3 to be able to get the other half, or the other part of our ratio. So that's 48.6. 48.75. So we've got 48.75 for our dominant expected and 16.25 for our recessive expected. So we're just going to go across. So 22 minus the 48.75 gets us the negative 26.75. And 26.75 for the bottom one there. Squared, each of those is going to be 715.56. So now we're going to take 715.56, divide it by our expected, which on top is 48.75. That gets us a value of 14.67. On the bottom, we've got 715.56, and we're going to divide by 16.25, which is 44.03. So added together, we have 14.65 plus 44.03. We have a chi-square value of 58.7. So a very large chi-square value. And again, we've only got 2 degrees of freedom. Or sorry, it's 2 minus 1. So 1 degree of freedom. So a chi-square of 58.7 with 2 degrees of freedom. We scroll up to our table here. We are well above the P of 0.01, since that's 6. So what that means is we are going to reject the null, and this is not a cross between 2 heterozygous. Because this says, you know, this ratio would be, yes, it is, but our chi-square says that by being very, very large says no, this is not, something else is going on. And because it's greater than, we are going to reject the null because, you know, there is very, very, very little chance that that ear or those P's were from, in this case, the predicted cross. So I've got one more here just to show you if you want to watch. So this one I've got, again, 3-to-1 ratio. And we've got purple is dominant over yellow, because this is, again, looking at corn from the lab. So 29 plus 13. Just walking through those steps again. So the first thing to do is to add together what you get. 42. 42 divided by 4, because we're working with the same ratio again. 10.5. Multiply that by 3. That gets us 31.5. (29) minus 31.5. So that's going to be 2.5 for each of these. So that's going to get us 5 for our square. or I'm sorry, 6.25. It's 5 if it's, yeah. Got too fast for myself. All right. So 6.25 divided by 31.5 gets us 0.198. And then the other one, 6.25 divided by 10.5 gets us 0.595. Whoop. Add those together. Gets us 0.793. And I can already tell you that that is below the threshold for our chi-square. Again, 1 degree of freedom, so 0.793. Go back up to the table. At 0.05, it's 3.84. And that's where we have that point. If it's below that, we don't look at it. So that means that these kernels are from that heterozygous cross. It is a 3-to-1 ratio, even though it doesn't quite look like it. It is according to this chi-square. Same thing as the one up here. That number, that chi-square number, is well below both of these numbers. And so we fail to reject the null hypothesis, saying it is from that cross. All right, hopefully that helps for those of you that these tables might be helpful for. If you have any questions on this using chi-square or the lab itself, let me know.